Ashish Garg. I know him from my school days. We were students together at Indian Institute of Science, Bangalore. He was my senior in the school.
1 year.
But yeah, so I had the chance to learn a lot from him because his advisor was Professor Ranganathan, one of the most famous crystallographer in India. I think he memorized everything about point groups and space groups, and he could actually draw. You just say that point group, just draw the whole structure on the board right away. And the whole lab was like that. They were modeling and designing crystals. So I used to be in that lab quite a bit, learning from these folks. I think from there, Ashish went on after ISC Bangalore to work at Cambridge. And he was doing his PhD in the area of thin films. So became experts in depositing not only ferroelectric but various other systems. And then after he came back to IIT Kanpur after his postdoc and PhD, he has developed very wide variety of, I think, so I visited his lab a couple of times at IIT Kanpur. First time it was all about thin films. Next time it was about energy harvesting, polymers, composites, including solar cells. And now he has formed the department, a new department at IIT Kanpur, which brings together all the energy researchers. And IIT Kanpur has a lot of centers and clusters related to energy. So I think this department will hopefully integrate all that expertise under one umbrella and bring together not only generation and storage portfolio, but maybe also conditioning and monitoring portfolio. So it's very, very exciting. And also I think it shows his caliber, that he's able to interact and communicate with very diverse audience. I also know Ashish is a very good administrator. I visited one time with him Delhi to meet Minister of Science and Technology. And so I had the chance to see how he really presents beautifully his research and convinces other people to make a big investment. So I think he will be a great department head and trying to lead this new initiative at IIT Kanpur. So thank you so much for taking all the time to visit us. Much appreciated. And we're all glad to listen to your seminar.
Thank you. Thank you, Shank. Well, it's a pleasure to be here at Penn State. This is my first visit to Penn State, and so I told Shashank that I'll either visit in Virginia Tech or somewhere wherever you are. I couldn't visit in Virginia Tech, but yeah. So here I am at Penn State. So well, my group basically works in ferroelectric materials, multiferroic materials. They're bulk forms and thin films. That was my primary interest when I joined for PhD in Cambridge in 1998. So Jim Scott was the one who energized and moved me in that area. So I remember reading his science paper of 1995 when I was doing a term project at ISC Bangalore. So that was when I got interested in ferroelectrics. And then I moved into, well, expanded into organic solar cells. And, you know, it comes around full circle. Perovskites were back in action in the solar cell form. So, so while we were doing oxide ferroelectrics, which are perovskites, we are now doing perovskites, which are non-oxide perovskites in solar cells. So this talk is about organic and perovskite solar cells. So part of the talk is about performance enhancement, and part of the talk is about stability issues in perovskites. So this is the new department that we have created. I'm a material scientist. I was a material science and engineering earlier. Now I have full-time moved into this department and we also have a Center for Energy Policy and Climate Solutions. So we are also doing some work on carbon neutrality, net zero kind of things. So those of you who don't know where we are in the northern part of India, about 450 kilometers east of Delhi and about 90 kilometers south of Lucknow. And it's a city with population of about 4 to 5 million, which is a lot of people considering the universities in the world. But and it was earlier famous for its textile industry during the British times and afterwards, but then those those industries have sort of gone away. This is where we are. We are 1100 acres campus. It can be, you've been there, Clive, so.
No, only virtually.
Only virtually?
Yeah,
Oh, okay.
unfortunately.
Okay. So we are about 10,000 students. We have a campus of about 1100 acres and we are 520 faculty members. And we have very, very prominent alumni base across the world of more than 40,000 alumni over years. So before I begin my talk, let me thank the funding agencies in India and overseas who have funded this research, and also some collaborators and my group members, some of my group members who have participated in this work. So let me just start with perovskite and organic solar cell. So perovskite organic solar cells are slightly different from typical PN junction solar cells that you see in silicon. So in these solar cells, generally what we have is we have see if I can turn the pointer on. Yeah. So in these solar cells, what we have is the main light absorbing layer is the active layer. We call it as active layer. So in case of organic solar cells, this active layer is typically a blend of a p-type semiconductor and n-type material. And in case of perovskite, it's generally just the perovskite material itself. So it's unlike silicon where you have to form a PN junction. Here, PN junction is formed due to different purposes, but perovskite is, for example, ambipolar material. It allows the transport of both electrons and holes, whereas in case of organic solar cells, you rely on the blend of P and N types materials for electrons and holes to be separated. What you require in these systems, other than that, so this absorber layer could be about 100 nanometers in case of organic solar cells, and it's about 0.5 micron to 1 micron in case of perovskite solar cells. This layer is sandwiched between the two layers. One is hole transport, electron transport layer. So hole transport function is to transport the holes from the absorber layer to the anode, but at the same time it blocks the electrons from going to the other side. Similarly, electron transport layer, it facilitates the transport of electrons from the absorber layer to the cathode. At the same time, prevents the flow of holes to the other electrode. So it's a very simple device structure. The good thing about this device structure is most of these layers can be solution processed. And you already know perovskite and organic solar cells, they are basically chemistry-based compounds. So you can easily tune their band gap, easily change their compositions and other optoelectronic properties. And since you can make them using solution processing, either on glass or on flexible substrate, they offer a lot of different kinds of applications, especially in conformal electronics. There are issues, however, with these materials that they, in case of organics, the efficiency is low. It's about 15–16% for single junction devices, well, which is high for organics, but it is low from the world standard of perovskite, which is about 25% at the moment, and even silicon is about 26% right now. The major issue with these two technologies is that one, their stability is very poor. They don't last in the ambient, depending upon where you are. I mean, if you're in India in monsoon season, they don't even last for a couple of days, but in summer and winter, they might be a little longer. And another problem with perovskites is presence of lead, which is an issue in their commercial realization at the moment. The good thing is that you can make these on either transparent glass substrates or plastic substrates, which actually enhances their application potential, especially for organic solar cells. And their processing temperatures are generally very low. That's again a very positive point from the perspective of thermal budget. So, I've split my talk in two parts. One is the organic solar cells. Second is the perovskite solar cells. So let me see. I mean, if we don't know what time, then we might skip the second part. But let me show you what we have done in organic solar cells to begin with. So organic solar cells, I mean, of course, they've been here for almost 20 years or so. We were working on organic solar cells typically on glass and plastic substrates, which are transparent in nature. But this was an interesting project that came from one of the industries, and that was Tata Steel. So while you can put organic solar cells on, transparent substrates for normal applications, the idea of Tata Steel was that can we integrate, so can we integrate a solar cell with the steel roof, which is used as a roofing material in India and in rest of the world in many parts quite extensively. The idea was that can we put a solar cell on top, and then solar cell can produce enough energy to light, for example, one small LED bulb, one DC fan, and one mobile charger. This is the bare minimum need that would be present, that would be for a household in, let's say, rural area or a hilly area. And why they wanted to do this project was because it would enhance the value addition of their steel roofs. Those steel roofs are generally used only as roofing material, but if you can provide this roof along with the energy source, then this could be a good value addition for Tata Steel itself. So this was the idea that can we integrate these organic solar cells on steel's roofs. So you can integrate in the form of building integrated photovoltaics, where you can depending upon the area that you have on the surface and the efficiency that you get, you can power certain appliances. So if you compare variety of materials, so first what we have to look is what are the comparative parameters of steel and glass as well as plastic substrate. So I put in three substrates here. One is typical glass substrate. Another is PEN, which is polymeric flexible substrate, and third is stainless steel. Now, if you look at comparative parameters, which are nice about steel, is steel processing temperature is very high. It doesn't degrade at low temperatures. It doesn't soften if your processing temperatures are high. It doesn't soften. Whereas glass and PEN, depending upon processing parameters, they have a tendency to soften, especially PEN. Steel also has comparative coefficient thermal expansion. It has very high elastic modulus. It could be resistance to oxygen and moisture depending upon the composition, and it has high electrical conductivity and high thermal conductivity. The bad thing about steel is its weight is on the higher side and it doesn't transmit any light. This is the major problem. The later part is the major problem, because weight is not too high when you compare a very thin film of steel, but the transmittivity is zero. So what do you do? Where do you get the light from? So this was a major challenge in going about this project. So why steel substrate? I've given you some heads up early, but so not only they want to commercialize this as part of solar cell integrated steel roof, apparently there is a significant cost reduction when you use steel as a substrate, which is about 25% cheaper as compared to TCO coated glass. And TCO uses indium, which is not really a very prevalent kind of metal. So as a result, there is an interest in making these solar cells on steel substrate. Other than that, there is a possibility of using steel as an electrode itself because it's conducting. And then steel also has excellent radiation hardness. So there are certain advantages to using steel in addition to excellent barrier properties for oxygen and moisture. So the challenges were, of course, the opaqueness, because we need to figure out how the light is going to enter the active layer. And then another thing about solar cells is whether you use an inverted design or a normal design. So inverted is, so if you take a device, in a normal device, when the holes move towards the substrate, then it's a normal device in case of organic solar cells. But if electrons move towards the substrate, then it's an inverted device. So that requires appropriate alignment of energy band alignment of different layers. So what kind of materials do we choose so that we have either an inverted or normal architecture, facilitating the flow of electrons and holes? Another problem with steel is the roughness of steel substrates is very high. You know how steel substrates are made? They just come out of cold rolling mill and they can be very high. And given that these layers are going to be only 100 nanometers thin, I mean, no way you can afford high roughnesses. Then, of course, there's a problem with rusting and pixelization. How do you pixelize the substrate? So there have been some work on these kind of things, but these were very pixelated solar cells, and also they used layers which were either, so it could be you can have either an inverted configuration where zinc oxide is put at the bottom, or you can have a normal configuration where you have P.PSS, which is a whole transport. So zinc oxide is an N-type oxide, so you can use it as an N-type layer, which means electrons will move to the bottom, or you can put P.PSS, which is a P-type material, and so that holes will move towards the bottom. So type A is the normal inverted architecture, type B is the normal architecture. So literature has shown that by using different polymers, one can achieve efficiencies of the order of about 2 to 3%. It really depends upon, but the problems with these were they used electrodes of silver, or they used electrodes by making grids of 2 or different compounds, quite cumbersome way of making electrode with lower transparency. So there's also, you can make tandem device, but tandem device far more difficult. I mean, single junction device itself is very difficult, but people have worked on tandem cells taking efficiencies of about 6%. And what we did in our work was we used a single layer device to achieve efficiency of the order of 6%. So what we did was we did some literature review as to what kind of materials will have aligned bands. And what we see is that if you use a steel substrate, you first will have to planarize it using a polymeric layer, which in our case was PMMA layer. Then we chose aluminum as a cheaper electrode, which could be coated easily on steel. Aluminum not only further planarizes the steel substrate, it also provides the N-type contact. And then since aluminum was going to be N-type contact, which means because the work function of aluminum is quite high, so that's why you cannot choose it as a hole collecting electrode. So now the next question was how to choose the electron transport layer, and we found that energy levels of zinc oxide match quite well with aluminum energy levels. So this is where we have the blend of P and N-type material, which is P3HT-PCBM, so polyethylene and the C60 compound. And then on top, we choose molyoxide as a P-type oxide to facilitate the flow of holes, and then we have gold electrode on top. So this is so in this device, it's a very simple device. So you just make everything by solution deposition except aluminum and molyoxide. So PMMA is made by solution, aluminum is made by evaporation, zinc oxide again solution processed, P3HT-PCBM is again solution processed, and then molyoxide could be solution processed or it could be evaporated, but in our case we evaporated it. So so this is your substrate that you get from company, which is a polymer coated Tata Steel substrate, which has a roughness of about 7 nanometers. We further made PMMA coating on this. This reduces the surface to about roughness to about 1.5 nanometers. And then, you did do the optimization of different electrodes. And what we find is that gold layer of about 16 nanometers is good enough, but it has a transmission of only 39%. And it gives you sort of moderate sheet resistance as compared to other thicknesses. So then we did a lot of optimizations for different layers. So this is, for example, for different gold thicknesses, we get efficiency of about 0.76. So you keep optimizing zinc oxide optimization, followed by, so if you do zinc oxide optimization, you get efficiency of about 1.1%. And when you do MOO3 optimization at a certain thickness of 3 nanometer, it's a very small thickness, because if you go to higher thicknesses, then your recombination at the hole transport layer is very high, and we could achieve up to 1.35%. And we did some modeling to find out the role of these thicknesses. And what we see from here is when you plot the optic electric field in the device as a function of thickness using a transfer matrix formalism, we see that for certain thickness. So idea is to maximize the field within a layer, optic electric field, because that is good for solar cell characteristics. And we find that for the chosen thickness, the optic electric field is maximized in the device. So for example, zinc oxide, it works out well in case of 30 nanometers. In other cases, the field is going down. But whereas in case of molyoxide, all the thicknesses work well, but practically speaking, 3 nanometer works better than other thicknesses. The problem is we still have lower transmission. We have only 39% transmission, which means 60% of the light is not going to be absorbed. What is the benchmark efficiency of P3HT-PCBM? We choose P3HT-PCBM because it's a workhorse material. Although it's not a high efficiency material, it helps us to optimize the processes. So how to increase the transmission was the next goal, because you're still losing 60% of light. With 100% transmission, you get about 3%. With 50%, you should get about 1.5%, and you get about 1.35%. So the question was, how do you increase these efficiency by increasing the transmission? So this is where we stumbled upon the idea of having these multi-layer electrodes on top. So apparently, if you dig into the literature, and you see that if you make metal dielectric stacks, by tuning the refractive index and the extinction coefficient of light, you can increase the transmission of top electrodes by making a multi-layer electrode than making just a single layer electrode. So what we did was, so the device configuration stays the same, but instead of using just gold layer, we put a top layer of moly oxide to make it a dielectric. So MOO3 basically is a dielectric. So dielectric metal dielectric stack that which results in higher transmission. So this is what basically the ground rules are. One, we need to choose a dielectric capping material which basically reduces the reflection of visible light from the top side. It should have high refractive index. Okay, so you should bend the light more and more to increase the absorption. Secondly, you should have low extinction coefficient of light in the thin film. So if you fulfill these two characteristics, then we should be able to get a transparent or more, electrode with a more transparency. So we chose two samples. This was a control sample without the top layer, and this was the top capping layer, the different sample. So when you do this with different thicknesses of moly oxide and gold, what we see is that when you put down different thicknesses of moly oxide, we see that our transmittance is maximum for 20 nanometer. This is because of optimization of the two parameters. And so we get about 95% transparency at about 20 nanometer, which reduces to 85% at 50 nanometer. And this is also evident in the reduced reflection from these layers. So moly oxide reduces the reflection. And these are fairly smooth films. However, for certain thicknesses, if you look at 40 nanometers, if you look at 50 nanometers, the surface toughness is very high. So we had to stick to lower thicknesses because the surface toughness is lower in case of thinner MO3 films.
What temperatures do you see for the processing of your capping moly?
So these are all, so you evaporate MO3, but the substrate is kept at room temperature. So it's not high temperature process.
Okay. So is there an impact on the crystallinity, or is it nearly all amorphous?
Well, they are sort of semi-crystalline. They are not really very crystalline.
Yeah.
If you heat treat them at high temperature, they tend to increase their roughness, which is not really good for the transmission characteristics.
So it's a challenge.
Yeah.
So it's all about thickness and just making sure you control the.
It is about thickness and the temperature of deposition. Yes.
Okay. Thank you.
So we did optical ellipsometry to understand N and K values, and what we found is that extinction coefficient of moly oxide film is lower than the gold film, and the refractive index is greater, which is a good thing because then you can absorb more light into the active layer by transmitting. Basically improves the light coupling in the device. So then we did further experiments by making stacks with different combinations of thicknesses, and we see that at about 16 nanometer of gold and 20 nanometer of moly oxide, we get lowest reflectance as well as transmittance is fairly comparable, except so if you look at all the samples at higher wavelengths, it does diverge, but at lower wavelengths, 16 to 20 nanometer. But we chose 16 to 20 nanometer mainly because of roughness. The roughness of the device was much lower. So, and another thing was not only the transmittance is important, but also important thing is conductivity of the electrodes, because if the conductivity is poor, then you won't be able to collect the carriers efficiently. So making measurements of pure moly oxide is not possible. It's very resistive in nature. But if you do if you do measure the resistivity of gold moly oxide stack, then we see that the lowest resistivity that we obtain is at 16-20 combination, which is 20 nanometers of moly oxide. One thing that we found is that why is that it leads to higher conductivity, and we did some XPS. What we find is that moly oxide has a moly valence is +6, so it goes to +4 state, and this +4 state leads to formation of oxygen vacancies, and these oxygen vacancies lead to higher conductivity of moly oxide capping layer film, which improves the charge collection. So when you make devices with these combinations for P3HT PCBM, we get efficiencies of 2%. So this is a significant improvement from 1.35 to 2%. And this is about 70% of what you obtain in a normal P3HT PCBM solar cell. And the device has considerably lower series resistance and fairly high shunt resistance, which are good things. And as you can see, if you look at the ratio of on current to off current, and this ratio is approximately 4 orders of magnitude, which is 10,000 is a good on-off ratio as compared to a device which has an on-off ratio of 100 or 500. But still, you can see that there is a problem. The problem is that the fill factor is still not perfect. I mean, in these devices we get fill factor about 40%. Whereas in a good organic solar cell device, you should be getting a fill factor of nearly 70% or 75%. So, and that's mainly because one, the resistivity of the components is high. Because you are using metal oxide on top, the resistivity is still high. As a result, your series resistance is high, and the shunts are also high because the aluminum is not a perfect electrode. It does provide problems with the bottom side in zinc oxide, leading to more recombination. What we did was then we used, instead of P3HT PCBM, we used a higher efficiency material, which is PTB7, and the PTB7 devices on glass give you efficiency of the order of 7 to 8%. And remarkably, when we make these devices with the top electrode consisting of this dielectric metal dielectric stack, this gives the efficiency of 6%. So 6 divided by 8 is approximately, it's a good number, getting close to 80%, maybe between 70 to 80%. So essentially what it says is that by making this dielectric stack, you are coupling about 70 to 80% of light, which is a lot of improvement as compared to plain gold electrode, which gives you 40% transmission. So by making this multi-layer electrode, you can improve the transmission of the stack by roughly 2 times and increase the light coupling or light absorption in the active layer. So by no means it's a perfect device as yet, because making steel has challenges, but we have been able to ramp up this efficiency for PTB7 to 6%, which is probably highest obtained on this substrate so far. So, I mean, you can also look at the problems in the EQE external quantum efficiency data. So, of course, at those thicknesses, the light absorption is much higher. So, if this is the absorption of light in the active layer. So, absorption of light is very high as compared to other thicknesses. And that is because of transmission of more light from the top electrode. And then EQE measurements show that you still have room for improvement. So devices show, EQE external quantum efficiency, which is how much light is converted. So we are still close to about 50% or so. You can improve that to 70% by further using transparent electrodes. You can use transparent oxide electrodes, but the problem is you will have to deposit them by sputtering, which will destroy the solar cell. So that is why we went for metal, dielectric metal stack, which could be made using processing, which do not destroy the bottom layer. Interestingly, the lifetime of these devices is also slightly better. So when you put a capping layer, the lifetime is slightly improved. It's not a remarkable improvement, but it's only a slight improvement in terms of all the physical parameters. So the most of the drop in these devices is mainly because of drop in the fill factor and the current. VOC is rather straightforward. It's constant. So it's because of material degradation, which to some extent can be circumvented by using these top electrodes, which are metal dielectric metal top electrodes. So, so this is about basically use of designing a transparent top electrodes for solar cell devices on steel substrates. And this is a challenging thing, because designing a top electrode which is transparent is not a trivial problem. And this is something which is important for perovskite and organic solar cells if you want to make them on opaque substrates. There are other issues that we need to understand. What about tandem devices? Can we use, see, we still use toxic solvents like chlorobenzene. Can we avoid using these toxic solvents in the processing? And there are still stability issues. So some of that work is still a work in progress, but these are the issues that still remain with these devices. So let me now come to the second part. How much time do I have?
Maybe about 10
minutes. Yeah, okay. So perovskite solar cells have been in the reckoning for about a decade, since 2019, when the efficiency was 3.9% as demonstrated in the first report. Today we are standing at 25%, which is a remarkable achievement in these 10 years or so. So perovskites, all of you are aware, I mean, it's a AbO3 kind of structure. And one of the important things about perovskite structures is this geometric tolerance factor, which is, the sum of A ion and the X ion divided by square root 2 into sum of B ion and an ion. Now here in these materials, different types of materials can take A site, different types of ions, not materials, can take A site or B site or X site. So X site is, unlike oxides, here the anion is the chlorine or bromine or iodine, one of the halogens, and the B site is typically lead, but it could be replaced by tin, for example. And similarly, the A side is methyl ammonium or formidimium or some other functional group that could go to A side. So these materials are very exciting because they give rise to efficiencies exceeding 25%, and material is ambipolar in nature. Earlier thought that perovskite was only unipolar, but later it was figured out that it's actually ambipolar material. So you don't have to use another blend, you don't have to blend it with other material to facilitate both kinds of transport. So that's a good thing about this material. So journey has been phenomenal, from 3.8% in 2009 to 25+% in 2022 on single junction devices. But in tandem device, if you make a device by combining two band gaps, then you can achieve more than 29% in combination with silicon. So perovskite device is very simple for those of you who were not aware. It's a simple device which is sandwiched between a TiO2, which is an N-type layer, and a whole transporting material, which could be spirometad or some other kinds of material. So essentially, TiO2 is the job of TiO2 is to transport electron to the anode, to the bottom side, and the whole transporting layer transports the whole to the top electrode. This layer in between, it's about 0.5 micron to 1 micron thick. And earlier it was impregnated with a variety of materials, but modern architectures simply use a thin layer of perovskite without impregnating it with anything else. So good thing about perovskite says it has high absorption coefficient, it has high diffusion length, you can solution process the devices, it has tunable band gap, cheap elements which are abundant in nature. But the problems are, one, stability. The solar cell stability is rather poor, and it's very, very variable depending upon the location. Hysteresis is another problem. So when you take the device in forward and reverse, there's a difference in the characteristics, which has been attributed to certain ion migrations in the devices. And then, of course, presence of lead, which presents a toxicity challenge. So there are several gaps in perovskite solar cells, despite all the progress that has been made. One is, of course, the presence of lead, which is an environmental hazard. And second is the structural instability. So perovskites have a problem of being structurally unstable, either whenever you apply heat or even light stress or moisture-related stress. So any kind of environmental stress makes a structure unstable, and perovskite tends to break into different compounds. And this is a very critical problem in perovskites. Hysteresis issue is shown on the right. So if you sweep your device in the positive direction or in the negative direction, some of the devices, if they have poor interfaces, then they tend to, or if they have ion migration issues, then they tend to have difference in forward and reverse, and which is not an acceptable thing. For a good solar cell, the reverse and forward characteristics, IV characteristics, should be nearly identical. And then the biggest problem is the poor lifetime, which could be because of moisture reactivity leading to formation of lead iodide. There are the intrinsic stability issues. Also, light causes instability in perovskites. When you apply high voltages or when you sweep it many times, then also it leads to heating of the device. And of course, there is also an issue of mechanical fragility. So all of these things, despite all the progress in perovskites, have not yet led to commercial realization of this kind of material. So one of the issues that we see in our lab is it's highly, there is a problem with reproducibility. So if you make several devices, the devices tend to show efficiencies which could be, on the higher side of 15 or lower side of 15, but the spread is large. So you get a bell curve which is pretty spread out. And then efficiency, of course, when you do measurements under high humidity or high temperature, then of course you see formation of secondary phases like lead iodide, and they lead to serious drop in the efficiency as a function of time. So there are ways to deal with it. I mean, people have tried a variety of compositions and processing varying process parameter. But the problem is if you look at compositions of perovskites, you have cesium, you have methyl ammonium, formaldinium, rubidium, and so on and so forth. There are at least 1,000 combinations to try, which is not a trivial job. Similarly, if you look at processing parameters, there are at least 10 processing parameters, which give you, nearly 10 or 10 combinations. So it's physically not possible to screen out everything. Then, of course, you have variability in band gap, which could be affected through an ion composition like bromine or iodine. So if you put in all this together, there are huge number of variables to be undertaken to solve these issues. And this is where I think the role of AI and machine learning becomes very important to screen out compositions and conditions which can give you a good process map. So for example, so this is where, as I was saying, machine learning with perovskites can be very useful in determining compositions which are suitable. And this area has seriously grown over past few years quite significantly. So
has it been a breakthrough? Has it generated a breakthrough?
There are some groups who have, for example, there's a group in Germany which has obtained good success with AI/ML, but still, I think the number of data points that they require to do AI and ML, that is still not there.
It's probably this bell code problem that you talk about here. So even though you could go through the compositional variations,
yes,
your variability is coming from basically humidity changes.
Variety of things. It could be humidity changes. It could
process.
Be yes. Yeah. So
So
this is a serious problem. So I mean, we have seen in our group that a lot of reports which are published in perovskites literature, many of the data are actually irreproducible. So this is a serious issue in perovskite literature, and how do you address that? That remains a challenge. So how do we solve these problems? I mean, these can be, so for example, enhancing reproducibility is an issue which has affected almost everyone. So people have tried various methods by using different additives and stuff like that to improve the reproducibility of devices. Other is how to incorporate materials which are stable and low cost. So for example, spirometad, which is the whole transporting layer, it's known for its degradability as well as its high cost. So people have looked at configurations which are inverted in nature, where we use solution processable oxides like nickel oxide and zinc oxides, which lead to higher stability of these devices. Not very stable at the moment, but still more stable as compared to those based on organic compounds. Other is use of 2D based perovskite solar cells. So, methyl ammonium lead iodide is a 3D perovskite. It has high efficiency but lower stability. So 2D perovskites, which are more horizontal structures, they have higher stability as compared to 3D perovskites. But the problem with 2Ds is that 2Ds have very poor efficiency. They tend to be more resistive, and they in terms of charge transport, they are worse as compared to 3D. So the concept is to mix 2D and 3D and make layers which can be reasonably conducting. With a slight compromise of efficiency, you can achieve higher lifetimes. So some groups are working on this kind of approach. Other approaches, perovskite thin films tend to have a lot of defects. Defects are hungry places for eating away your holes and electrons. So how do you passivate those defects? The concept is very similar to what you saw in amorphous silicon, where you put in hydrogen to passivate the defects. Here you use different kinds of additives. So these could be organic additives, inorganic additives, different compounds which sit in traps, and they basically passivate the traps and grain boundaries in these materials. So different sorts of models are possible. You can have point defects, or you can have grain boundary defects, or you can have microstructural defects that can lead to passivation. And depending upon what you use, the use of additives can actually make solar cells last fairly long as compared to the ones which don't use additives. And there are other methods like strain engineering and using different transport layers to control the ion migration. You can do interface engineering. Again, interface engineering and strain engineering are fairly analogous concepts, but you can introduce the strain in the perovskite layer to modify its crystal structure as well as the carrier transport. Then, of course, so these are fairly similar concepts which make changes either to the active layer or to the microstructure by passivating the interfaces or passivating the grain boundaries. So let me just go to what we do. I'll show you some highlights of our work. So for example, one of the works that we have done in our lab is to increase the conductivity of bottom TiO2 layer. So titanium oxide is, as you know, it has rutile and anatase phases. Titanium oxide is not very conducting. Okay, it's an N-type material, but it's not very highly conducting. So when you dope tantalum into TiO2 lattice, tantalum is +5 element. Okay, so it causes N-type defects. It increases the electron density in TiO2 layer. So what we find is that the improvement in the conductivity of TiO2 is about 5 times when you incorporate tantalum in this lattice. Second good thing that we obtain is that our hysteresis is almost vanished. The devices without tantalum doping of TiO2, they have higher hysteresis, but here the hysteresis goes down. And we also obtain higher fill factor as well as performance of the devices. So this was very early work that we did on methyl ammonium lead iodide to basically show that by tweaking the defect chemistry of TiO2. TiO2 is an oxide, so oxides are, if you know defect chemistry, you can easily tune their electronic properties by controlling the amount of defects that you have in them. And the doping level is about 0.3% or so, 3 mole percent, sorry, 0.3. We've also looked at processing temperature reduction. So generally, the TiO2 that you process in the lab as a full electron transport layer, it's about 500 degrees centigrade processing in the laboratory, which is fairly high. Most of the glasses soften at this temperature, so it's not really it's not a very desirable thing. So what we did was, instead of doing high temperature thermal processing of TiO2 on hot plate or in furnace, we did microwave annealing of TiO2, and this microwave annealing is only for a minute or two, and this does wonders. The temperature measurements, of course, are not very accurate on microwave, but whatever optical methods we have tried, and they seem to be lower as compared to the one in TiO2. The important thing is about the device efficiency improvement. The device efficiency improved by about 3% or 4% in case of microwave process sample. Another thing that we see is that when you process TiO2 using microwave process, the grain size of perovskite on this is very large, and that leads to lower recombination in the device. And also, microwave TiO2 leads to a better texturing of perovskite thin films. We did some analysis based on our electrical measurements as well as optoelectronic measurements, and we find that the defect density in microwave processed TiO2 is lower as compared to the one which is not microwave processed. So overall, the efficiency is better, stability is slightly better, It's not that it's very highly improved. TiO2 doesn't really affect the stability that much, but still the drop of efficiency is, so you see in 2500, we get about 20% drop in case of microwave TiO2, but in case of other film, we get 40% drop, which is significant improvement because TiO2 in the end affects the traps in the active layer, and traps in the active layer affect the stability of perovskites. Another thing that we have done is to look at whole transporting materials which can replace spiro. So we look, I'll just on the last slide. So we have looked at alternate whole transport materials as to replace a spiro omitad, and we find they're not very high performing, but they can give you efficiencies between 10 to 15% based on these donor acceptor donor kind of configurations of organic materials. And these are also synthesized. See, the problem with spiro is it takes long time to process spiro, and it's also very degradable and it's expensive. So these materials are cheap, they're not expensive, they can be made easily in the laboratory, and they are low temperature materials. Finally, this is the last slide. So we have also done additive engineering by adding additives to perovskite. So in this work, we have added PCBM, which is C60 molecule, into the perovskite layer. So generally, people believe that PCBM doesn't work as an additive, but here we have purposefully used it as an additive, and we found that using PCBM leads to stability of the device by about 20% or so. So the reason for this is, one, it leads to larger grain size in the perovskite film. It tends to improve the grain size to reduce the recombination, and we increase the efficiency by about 15% and leading to better stability. So effectively, basically reducing the trap density in the material. Second is we use additive to increase the grain size. So if you use ammonium chloride, and this is about the role of chlorine. When you put a little bit of chlorine in the perovskite lattice, it goes to the grain boundaries and changes the grain boundary energy in a positive way, so that the grain size, if you notice this one without the additive and with the additive, the grain size is significantly larger. And this leads to significantly improved performance, not only the efficiency, but also the lifetime. And this is, by the way, on methyl ammonium lead iodide. There is no other composition modification. So these are good efficiencies that we have obtained by, especially the lifetime, that higher lifetime can be achieved by reducing the defects in active layer, which could be either through modification of electron transport layer, or by adding additives, or by doing other kind of microstructural engineering. Finally, we also work on tandem solar cells. So we have modeled these tandem solar cells. So tandem is nothing but you have a solar cell device wherein a high bandgap material is at the bottom, and the low bandgap, high bandgap material is on the light side, whereas the low bandgap material is on the other side. So light enters from the bottom side. The short wavelengths get absorbed in the first layer, and the long wavelengths get absorbed in the top layer. So this should give you higher efficiency. So basically, what we have done is, most of the people who have modeled tandem solar cells, they have modeled them using only optical model. So here we have brought in the concepts of drift and diffusion, combined the optical model with the optoelectronic model, and we have been able to predict better match between the experimental efficiencies and the optimally desired efficiencies in perovskite by bringing optical and electronic models together. So we have shown that if you vary thicknesses, if you vary mobilities, you can achieve, you can find the sweet spots in the perovskite map. So for example, here we do the mobility variations by an order of magnitude of so, and we see how the sweet spot shifts in the perovskite solar cells, and accordingly you can choose the thicknesses of different semiconductors in the device. So this is a very nice piece of work when one of our students did recently. So there are still a lot of things. For example, people don't really understand the defect chemistry in these, and often I have seen that defect chemistry people get it totally wrong, because they are not familiar with what is a p-type oxide, what is an n-type oxide, what should the compensating defects. So I have seen perovskite literature which often has very not very accurate models of explaining the change in behavior when you process certain oxides. So role of defect chemistry is not yet very well understood. And also compositional control, tuning of interfaces, adding buffer layers, mixing 2D, 3D perovskites. It is something which is still very important. And what is very important is, extremely important, in fact, is the stability improvement of perovskite solar cells, which is still a thing in progress. And while we have a lot of indoor data, we still don't have much of outdoor data, especially in countries where conditions are significantly variable over a year. Countries like India, which sees like 4 seasons. And of course, these issues are again very real. They have significant variations in performance as you scale them up. The pixel to pixel performance varies quite a lot. The series and shunt resistances change. And another thing that we should worry about is use of non-toxic solvents. How can we promote that? Because most of the solvents are still chlorinated, which are not really the. And then, of course, there are still issues related to printing. And so one of the things with the group in Germany, as I was mentioning, doing is they are automating the process. So reducing the human errors and automating the process for optimization of these solar cells, which is very important thing. And we are also developing such a facility in our institute to automate so use a robotic arm to do the processing of perovskite solar cells, which would probably improve the repeatability of these devices. With this, thank you very much. If you have any questions, I'll be.
Just have some curious thing. In the past part of the talk, molybdenum oxide study. So is there anything else studied? I'm just curious.
So, I mean, we have been studying organic solar cells for a very long time, and we find moly oxide as a very good hole transporting material. So that is why we have used. Otherwise, you can use nickel oxide. That's also a possibility. But nickel oxide processing is a complex affair. You have to anneal nickel oxide at high temperature, and if you anneal nickel oxide at high temperature, it will kill the organic layer. So moly oxide, because you can keep the substrate at room temperature, and it doesn't kill the device. It's only 3 nanometer thin film, so you don't really expose it to the vapors for a very long time. Whereas in case of nickel oxide, you have to either evaporate it or sputter it, but sputtering evaporation of nickel oxide is difficult than moly oxide. So you have to use solution processing. The moment you use solution processing, you have to go to temperatures more than 250, which are not good for the bottom layer.
I have a question. On the first part of where you demonstrate the making thin film layer on the steel sheet. My question is, since steel is metallized and it has high thermal conductivity and good thermal expansion with solar light heat. So when we make very thin film of some oxides, then it is quite possible with day and night thermal cycle, this gets stress and compress. And when it happens, significant when the thin film is nanometer, there is finite chances of formation of cracks or.
No, there is a possibility. We don't, I mean, especially in a country like India where temperatures can vary, surface temperatures can vary significantly. There is a possibility, but the good thing is at the bottom we have polymeric layers. So we have 2 polymeric layers and the aluminum electrode. All of these are soft materials. As a result, they are able to handle the stress better in comparison to if you had a hard layer in between. Yeah.
So, after you, please.
So in your, by the way, very nice talk. And one other thing I really liked is the use case of solar on the roofing material itself, right? So
that was an interesting project for us also.
yeah. And in one of the slides, you were saying the resistivity of this gold deposited layer.
Yeah.
Can you go back to
Yeah,
this?
yeah. Sorry, I'll just see. Is that the one?
Electrical resistivity data.
Resistivity data. Hang on.
number.
Is that the one?
Yeah, yeah. So
Let me see if I can share this.
okay. So in gold, the electrical resistivity seems to be quite high, it's even higher than
Yeah,
the
so
bulk value. Is it because of the dimensional effect? Or?
it is because of its very thin, and also at this thickness, it's not a very continuous film. It is sort of
I
semi-continuous.
was
film.
expecting that would increase the resistivity, not decrease the resistivity. Which,
No, so well, I mean, resistivity is high, isn't it? So 307 is a fairly high number for.
then the bulk is -8, 2.2 -8 roughly.
Yeah, so this is the 370
One
-9.
one minus 8. let's say,
Yeah,
right?
so it's about you can say 30 into 10⁻⁸.
Yeah.
So this is higher resistivity when you make it very thin and it becomes discontinuous. So it is very close. So if you go below 16, you cannot measure them. So this is sort of the limit that we have hit.
Okay. Yeah. And the short question. Okay, so I think this dye sensitized solar cell, they have been
Yeah.
used in sort of similar application on
Yes.
tiles and all of those. Did you look into that as well, or?
No, we haven't worked on dye sensitized solar cells. It's a different beast altogether. So, but yeah, I mean, perovskites are very similar to dye sensitized, to be honest.
Yeah.
Yeah, but we don't work on dye sensitized solar cells. They are good for indoor applications, actually. Recent work has shown that they are very good for indoor applications, but not so good for outdoor applications.
I've been reading some literature. They make some kind of paint and they could just.
Yeah, it's a simple device. That's why it's very exciting.
Yeah.
But I mean, perovskite has trumped most of these materials.
Yeah, so thank you very much. It was really interesting talk. It's not totally my area, but there's a few things I've got to say.
Sure.
I'm amazed that you saw reliability basically being improved by basically just putting another donor into the titanium
Yes.
oxide. I mean,
Yeah.
particularly when you talked about where some of the mechanisms are that you
Right.
think they've got ionic migration,
Right.
and we
Yes.
know that maybe hydroxides and other things like
Mhm.
that can impact it. Can you explain a little bit why that TiO2 layer is really having an impact on reliability?
So TiO2 layer, see the kind of TiO2 layer that you have at the bottom that affects the microstructure of perovskite layer.
So it's templating
So,
the microstructure.
yes.
So it's another
So
microstructure.
essentially, it's controlling the grain size and traps.
Yeah. I can see the Fermi level of pinning, but then
Yeah.
then it's like, well, it's pinned, and then why is it then why is it then stable? But if it's changing the microstructure, then I
Yes.
can see the
Yes.
connection.
Yes.
So in that case, you pointed out that the defect chemists are getting this wrong, and I can understand why that is so, because it's not so easy to write down
Right,
these
right.
organic species.
Yeah.
But has people stepped back and even said, as a function of reliability,
Yeah.
have people looked at, say, the transference number? So you start looking at then the changes to then give a clue
Correct.
of what that speciation is that's problematic. Are you then seeing an increase in the ionic components
Yes.
with time?
So
Do people know that?
that's a very good question, and you know, the transference number, which is, you know, the ratio of ionic or electronic conductivity, total conductivity, that is something, those kind of studies are very few, very few.
It seems like it would be
And
quite easy to do.
It would be
right?
easy and interesting to figure out those mechanisms. But yeah, I mean, you're right. It has not been addressed. So most people focus on device fabrication and doing the typical device characterization, and a lot of this characterization is optoelectronic time-dependent characterization. In fact, this thing to figure out the defect chemistry using such methods is something which is very rare. There have been maybe one or two, maybe few studies. I can't count how many, but very few, very few. And this is an area where I don't find explanations very convincing at the moment.
Yeah, so a combination of some good impedance or some other forms of looking at the transference number, and then combining that with, I don't know, IRIFM or something like that, would be very informative.
Absolutely. Absolutely.
At the end of the day, even though you push these numbers out, we needed to go out to 10 years plus.
Absolutely. Yeah. No, you're absolutely right. I fully agree with you. And I think that is something which we should do, but students are motivated more by the numbers than by these.
But the numbers on reliability could be game changing.
Absolutely. If you change the reliability, that's a game changer.
We would take half that efficiency for a decade of stability.
Absolutely.
Any day.
Fully agree.
Questions on the Zoom? Anyone has a question? I think you can.
Is there anybody on Zoom?
There aren't any chats, so I don't know if anyone else has anything to add.
Another question?
That takes time. Yeah. So if I don't know if I understood correctly, on the first part of the door, the steel. So it was studied on the device was on top of the steel or behind the steel?
Well, we just made one side, so you could take either side. And so what we later did was so I'm not sure with that part, but we integrated a white OLED with the so on one side of steel sheet we had the solar cell, on the other side we had a white OLED device which we made in our lab. So what we could do was the idea was to power this white OLED using the solar cell on top, but the white OLED part didn't go very well. So we just tried some LEDs and they sort of worked.
Yeah, I'm wondering because you showed in your cartoon right at the beginning, which was I absolutely agree with Betty. It's like a very interesting idea of putting it on there. But you got corrugation, so you probably did all the experiments on just planar
On the planar devices.
But the corrugated form is going to be
so corrugated forms
complicated,
will also take different processing. So we are making using spin coating.
Yeah, there to be some sort of spray technology.
Either spray technology or I don't know, maybe slot die or something will work.
Yeah.
But that is something was for Tata Steel to figure out. We got a project to do on 4-inch substrate, which we did.
Just check chat and see if there is anything.
Yeah, okay. There's a question.
She said answer most questions.
Okay, there is no.
All right. Thank you so much, everyone.
Thank you.
Thanks everyone on the Zoom
Thanks,
also
everyone.
for joining in.
Thank you. Thank you, everyone.
Thank you.
All right.